Imagine standing on the edge of a cliff, staring into an abyss so vast that it swallows not just light, but understanding itself. Now imagine that this abyss isn't beneath you, but all around you, permeating every inch of space between the stars, between galaxies, between the atoms in your own body. This isn't science fiction. This is the reality we've discovered we're living in. Right now, as you listen to these words, an invisible force is literally tearing the universe apart at an accelerating rate, and we have absolutely no idea what it is. We call it dark energy, and it makes up nearly 70% of everything that exists. Think about that for a moment. 70% of our universe is composed of something we cannot see, cannot touch, cannot detect directly, and fundamentally do not understand. It's as if we've spent our entire existence living in a house, only to discover that 70% of that house exists in a dimension we cannot perceive. What does that say about the nature of reality itself? What does it say about how much we truly know about the cosmos we inhabit? The story of dark energy begins not with its discovery, but with a mistake, or rather, what one of history's greatest minds considered his biggest blunder. Picture this. It's the early 20th century, and Albert Einstein is wrestling with the equations of his newly developed theory of general relativity. These elegant mathematical formulas describe how mass and energy warp the fabric of space-time, creating what we experience as gravity. But there's a problem. When Einstein applies these equations to the universe as a whole, they predict something unsettling. The universe, according to his calculations, cannot be static. It must either be expanding or contracting. But in Einstein's time, everyone believed the universe was eternal and unchanging, a vast cosmic arena that had always existed in essentially the same state. Einstein trusted the prevailing wisdom of his era more than his own revolutionary equations. So he did something that seemed reasonable at the time but would haunt him for the rest of his life. He added a term to his equations, a mathematical fudge factor he called the cosmological constant. This term represented a mysterious repulsive force that counteracted gravity on cosmic scales, allowing the universe to remain static. Einstein had invented, purely as a mathematical necessity, a form of anti-gravity. But the universe had other plans. In 1929, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made an observation that would shatter the ancient conception of a static cosmos. By carefully measuring the light from distant galaxies, Hubble discovered something extraordinary. These galaxies weren't standing still. They were moving away from us. More precisely, they were all moving away from each other. And here's the crucial part. The farther away a galaxy was, the faster it was receding. Space itself was expanding, stretching like a balloon being inflated, carrying galaxies along with it. When Einstein learned of Hubble's discovery, he reportedly called his cosmological constant his greatest blunder. He had been so close to predicting the expanding universe from pure mathematics alone, but he had let prevailing assumptions cloud his judgment. The cosmological constant was abandoned, relegated to a footnote in the history of cosmology. Or so everyone thought. Fast forward to the late 20th century. By this time, cosmologists had developed a sophisticated understanding of the expanding universe. The Big Bang Theory explained that the universe began in an incredibly hot, dense state approximately 13.8 billion years ago and had been expanding ever since. But there was a crucial question that needed answering. How fast was the universe expanding, and more importantly, was that expansion slowing down? Logic suggested it should be. After all, every galaxy contains vast amounts of matter, and matter generates gravity. Gravity pulls things together. So the expansion of the universe, driven by the initial impulse of the Big Bang, should gradually be slowing down due to the gravitational attraction of all the matter pulling back. The question wasn't whether the expansion was decelerating, but by how much. This wasn't just an academic question. The rate of deceleration would determine the ultimate fate of the universe. If there was enough matter, enough gravitational pull, the expansion might eventually stop and reverse, leading to a big crunch, where the universe collapses back on itself. If there wasn't enough matter, the universe would expand forever, gradually growing colder and more dilute in what's called the Big Freeze or heat death. To answer this question, two teams of astronomers embarked on ambitious observational campaigns in the 1990s. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both racing to measure the deceleration of the universe. Their tool of choice was a particular type of stellar explosion called a Type Ia supernova. These cosmic detonations occur when a white dwarf star, the dense remnant of a sun-like star, accumulates too much matter from a companion star and explodes. What makes Type Ia supernovae so useful is their remarkable consistency. Each explosion releases roughly the same amount of energy, making them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. By measuring the distance to these supernovae and comparing it to their redshift, which indicates how much the universe has expanded since the light was emitted, astronomers could map out the expansion history of the universe. Both teams meticulously gathered their data, observing supernovae in distant galaxies, some so far away that their light had been traveling for billions of years before reaching our telescopes. They double-checked their measurements, refined their analysis, and prepared for the expected result, a universe whose expansion was gradually slowing down. But when the results came in, they showed something that made absolutely no sense. The expansion of the universe wasn't slowing down. It was speeding up. Imagine throwing a ball into the air and watching it not slow down as it rises, but instead accelerate upward, faster and faster, as if some invisible force was propelling it against gravity. That's essentially what these astronomers had discovered was happening to the universe itself. The initial reaction was disbelief. These teams had expected to measure the rate at which cosmic expansion was decelerating, and instead they found acceleration. It seemed impossible. They checked for errors in their observations, in their analysis, in their assumptions. They looked for any possible explanation that didn't require rewriting our understanding of the universe. But the data kept telling the same story. In 1998, both teams published their shocking findings. The universe's expansion was accelerating, and had been for roughly the past 5 billion years. This discovery would earn Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, but it also created one of the deepest mysteries in all of science. What could possibly be causing this acceleration? Gravity, as we understand it, is always attractive. It pulls things together. It should slow the expansion, not speed it up. For the universe to be accelerating, there must be some form of energy pervading all of space, an energy that generates a kind of repulsive gravity, pushing space apart. Scientists dusted off Einstein's old cosmological constant and gave this mysterious phenomenon a new name: dark energy. But naming something doesn't mean we understand it. In fact, dark energy might be the most profound indication of how little we truly comprehend about the universe we inhabit. Let's consider what we're really saying when we talk about dark energy. We're proposing that empty space, the vacuum itself, possesses energy. This isn't entirely foreign to physics. Quantum mechanics, the theory that describes the behavior of particles and forces at the smallest scales, predicts that the vacuum is not truly empty. Instead, it's a seething foam of virtual particles constantly popping into and out of existence. These quantum fluctuations should give the vacuum a certain energy density, and energy, as Einstein taught us with his famous equation E equals mc squared, is equivalent to mass. Mass and energy both generate gravity, and in the strange mathematics of general relativity, a sufficiently intense energy density can actually create a repulsive gravitational effect. This sounds like a perfect explanation for dark energy, except for one catastrophic problem. When physicists calculate what the energy density of the vacuum should be based on quantum mechanics, they get a number that is approximately 10 to the power of 120 times larger than what we observe as dark energy. That's a 1 followed by 120 zeros. This isn't just being a little bit off. This is being wrong by a margin so vast it's almost incomprehensible. It's been called the worst prediction in the history of physics. Ask yourself this: what does it mean that our two most fundamental theories of physics, quantum mechanics and general relativity, are so spectacularly incompatible when it comes to predicting the energy of empty space? These are the theories that have been tested to incredible precision in countless experiments. Quantum mechanics has been verified to accuracies of better than 1 part in a billion. General relativity has passed every test we've thrown at it, from the bending of starlight during solar eclipses to the recent detection of gravitational waves. Yet when we try to combine them to understand dark energy, we're off by a factor of 10 to the power of 120. This suggests that something is fundamentally wrong with our understanding of physics at its deepest level. Either quantum mechanics is incomplete, or general relativity breaks down in ways we haven't yet recognized, or there's some entirely new physics that we're missing. The existence of dark energy is telling us that we don't have the full picture, not even close. So what exactly is dark energy? The honest answer is we don't know. But we have several hypotheses, each with its own profound implications. The simplest possibility is that Einstein's cosmological constant was right all along, just not in the way he intended. Perhaps space itself has an inherent energy density, a property of the vacuum that causes it to push outward. This energy would be perfectly uniform, the same at all times and all places. It would be a fundamental constant of nature, like the speed of light or the strength of gravity. If this is true, then dark energy is simply a property of spacetime itself, woven into the fabric of reality. But this explanation, while mathematically simple, doesn't answer the deeper question of why the cosmological constant has the value it does. Why is it so incredibly small compared to what quantum mechanics predicts, yet large enough to dominate the universe today? This is known as the cosmological constant problem, and it's one of the most vexing puzzles in theoretical physics. There's another possibility, one that's potentially even more unsettling. What if dark energy isn't constant? What if it changes over time or varies from place to place? In this scenario, dark energy isn't a property of space itself, but rather a field that fills space, similar to how magnetic or electric fields permeate regions of space. Physicists call this hypothetical field quintessence, named after the fifth element proposed by ancient Greek philosophers. If dark energy is quintessence, then its strength and behavior could evolve as the universe ages. This opens up a range of possibilities for the fate of the universe that are far more dramatic than the slow heat death predicted by a cosmological constant. Imagine a universe where dark energy gradually becomes stronger, accelerating the cosmic expansion at an ever-increasing rate. Eventually, this acceleration could become so violent that it would tear apart not just galaxies and stars, but eventually planets, molecules, atoms, and even the fabric of spacetime itself. This apocalyptic scenario is called the Big Rip, and if dark energy is quintessence with certain properties, it could happen in as little as 20 billion years. Alternatively, quintessence could weaken over time, allowing gravity to eventually win out and possibly leading to a big crunch after all. But perhaps we're thinking about this entirely wrong. Maybe dark energy isn't a thing at all. Maybe what we're observing isn't evidence of a mysterious energy filling space, but rather evidence that our theory of gravity, general relativity, breaks down on cosmic scales. After all, general relativity has been exquisitely tested in our solar system and in extreme environments like near black holes, but testing it across billions of light years is a different matter entirely. Some physicists have proposed modified theories of gravity that would reproduce Einstein's predictions on small scales, but behave differently across vast cosmic distances. In these models, gravity becomes weaker on the largest scales, which could make distant galaxies appear to be accelerating away from us even without any dark energy. These modified gravity theories are mathematically complex and face their own challenges, but they represent a fundamentally different approach to solving the mystery. Instead of adding a new component to the universe, they suggest we need to revise our understanding of one of the fundamental forces of nature. Here's where the mystery deepens even further. Dark energy isn't the only invisible component of the universe we've discovered. There's also dark matter, a different form of unseen substance that reveals its presence through its gravitational effects on visible matter. Galaxies rotate faster than they should based on the mass of their visible stars and gas, suggesting they're embedded in huge halos of invisible matter. Clusters of galaxies contain far more gravitational mass than we can see. The pattern of galaxies spread across the universe reflects the gravitational influence of dark matter in the early universe. Between dark matter and dark energy, the ordinary matter that makes up everything we can see, stars, planets, gas, dust, and ourselves, accounts for less than 5% of the universe. 5%. Everything humanity has ever observed directly, every star in every galaxy we photographed, every atom in every living thing on Earth, all of it is just a tiny fraction of what exists. We are living in a universe dominated by phenomena we don't understand. Take a moment to really absorb that. The atoms that make up your body, the same kinds of atoms that compose stars and planets, represent less than 5% of the universe's total content. You are made of the minority component of reality. The universe is dominated by dark matter, which we can detect only through gravity, and dark energy, which we've inferred only through the acceleration of cosmic expansion. What does this say about our place in the cosmos? For centuries, scientific discoveries have progressively displaced humanity from the center of the universe. We learned that Earth isn't the center of the solar system, that our sun is just one of hundreds of billions of stars in our galaxy, that our galaxy is one of hundreds of billions in the observable universe. Now we've learned that even the type of matter we're made of is just a minor constituent of reality. We are not just small in size and scale. We are made of a cosmic afterthought, the universe's rounding error. The implications of dark energy extend far beyond humbling our cosmic perspective. Dark energy determines the ultimate fate of the universe, the destiny of everything that exists. Let's explore what happens as dark energy continues to drive the accelerating expansion. Right now, we can observe galaxies billions of light years away. The most distant galaxies we can currently see had their light emitted when the universe was only a few 100 million years old. But as the universe continues to expand at an accelerating rate, more and more of the universe will slip beyond what's called the cosmic horizon. Light from these regions will never be able to reach us because the space between us and them is expanding faster than light can travel through it. This doesn't violate the speed of light limit because it's space itself that's expanding, not objects moving through space. Over trillions of years, if dark energy remains constant or grows stronger, galaxies outside our local group will accelerate away from us until they vanish beyond the cosmic horizon. Future astronomers living in the distant future, assuming any exist, would see a far lonelier universe than we do. Imagine an astronomer living 100 billion years from now. By that time, if current trends continue, nearly all galaxies beyond our own local group will have receded so far and so fast that their light can no longer reach us. The Milky Way and Andromeda galaxies will likely have merged into a single large elliptical galaxy. Any beings in such a galaxy, looking out into space with even the most powerful telescopes imaginable, would see nothing but darkness beyond their own galaxy and perhaps a handful of nearby companions. The cosmic microwave background radiation, that faint glow of light left over from the Big Bang that has been so crucial to our understanding of cosmology, will have been stretched to such long wavelengths by the expansion of space that it would be utterly undetectable. These future astronomers would have no evidence of the Big Bang. They would see a universe that appears static and eternal, consisting of only their own galaxy surrounded by infinite darkness. They would have no way of knowing that they lived in an expanding universe, no way to discover dark energy, no way to reconstruct the history of the cosmos. The evidence would have literally expanded beyond their reach. What crucial evidence might have already expanded beyond our reach? What discoveries about the early universe are now impossible because the relevant information has been carried away by cosmic expansion? But the long-term consequences of dark energy become even more stark when we consider timescales of trillions upon trillions of years. Stars, including our sun, don't burn forever. They fuse lighter elements into heavier ones, releasing energy in the process, but eventually they run out of fuel. The Sun will exhaust its hydrogen fuel in about 5 billion years, swell into a red giant that engulfs the inner planets, and finally collapse into a white dwarf that will gradually cool over billions of years. Massive stars die more quickly, exploding as supernovae and leaving behind neutron stars or black holes. The smallest, dimmest stars, the red dwarfs, burn so slowly that they can continue shining for trillions of years. But even they will eventually exhaust their fuel. In roughly 100 trillion years, the last stars in the universe will flicker out, leaving behind a cosmos populated only by dead stellar remnants. White dwarfs, neutron stars, and black holes, along with planets, asteroids, and diffuse gas. This is the beginning of what's called the degenerate era, a universe growing dark and cold. As time marches on into the almost incomprehensible future, even these remnants won't last forever. Over enormously long timescales, of 10 to the power of 30 years or more, a process called proton decay may occur. If protons are not absolutely stable, and many theories in particle physics suggest they might not be, then even atoms will eventually disintegrate. The white dwarfs and neutron stars, made of matter held together by atomic nuclei, would gradually evaporate into radiation and exotic particles. If this happens, matter as we know it would cease to exist. The only significant structures remaining would be black holes. And yet, even black holes are not eternal. Stephen Hawking discovered that black holes emit faint radiation due to quantum effects near their event horizons, a phenomenon now known as Hawking radiation. This causes black holes to very slowly evaporate, losing mass over time. The rate is extraordinarily slow. Supermassive black holes with masses millions or billions of times that of the Sun would take 10 to the power of 100 years to evaporate. But given enough time, every black hole in the universe would eventually disappear in a final burst of radiation. This ushers in the dark era, a universe containing nothing but an increasingly dilute sea of photons and exotic particles, growing ever colder and more dispersed as space continues to expand. This is the heat death of the universe, the ultimate consequence of the second law of thermodynamics combined with accelerating expansion driven by dark energy. All structure, all complexity, all life, all thought, everything that could possibly be considered interesting or meaningful, would be gone. The universe would reach a state of maximum entropy, a perfectly uniform distribution of energy that cannot support any processes or changes. Time itself, in any meaningful sense, would cease to have relevance because nothing would be happening. No change, no events, no history, just an eternal, unchanging void that was once our vibrant cosmos. And this isn't scheduled for the distant future. This is what current cosmology, based on our understanding of dark energy, predicts as the ultimate fate of reality. How does it feel to know that everything, not just humanity, not just Earth or the Sun, but every galaxy, every star that will ever shine, every possible civilization that could ever arise, all of it is temporary, and the universe is destined for a cold, dark, eternal emptiness. Unless, of course, dark energy doesn't remain constant. If dark energy is quintessence and its strength is changing over time, the fate of the universe could be very different. Consider the Big Rip scenario mentioned earlier. If dark energy grows stronger over time, the acceleration of cosmic expansion would intensify. Currently, dark energy dominates on the largest scales, but gravity still holds galaxies, solar systems, and certainly planets and atoms together. But if dark energy continues to grow, there could come a time when its repulsive effect overcomes even these stronger forces. First, galaxy clusters would be torn apart, with individual galaxies flying away from each other at incredible speeds. Then, as dark energy grows even stronger, individual galaxies would be shredded, their stars flung into the void. Solar systems would be next, with planets ripped away from their suns. Eventually, the growing dark energy would overcome the electromagnetic forces holding molecules together, tearing apart planets, rocks, and every solid object. Microseconds before the end, atoms themselves would be ripped apart, their electrons stripped away from nuclei. Finally, Even atomic nuclei would be destroyed, quarks torn away from each other. In the final instant, space-time itself would be shredded in a catastrophic event that would mark the end of the universe as we know it. The mathematics that describe some quintessence models suggest this could happen in a finite time, perhaps 20 billion years, perhaps more, perhaps less. There would be no warning, no way to escape. The universe would simply tear itself apart from the largest scales down to the smallest. This is perhaps the most violent end imaginable for our cosmos. Alternatively, if dark energy weakens over time, gravity might eventually regain dominance, causing the expansion to slow, stop, and reverse. The universe would collapse back on itself in a big crunch, growing hotter and denser as all matter converges. This mirrors the Big Bang, but in reverse, ending in a singularity of infinite density and temperature. Some cosmological models suggest that such a crunch might even trigger a new Big Bang, leading to a cyclic universe that expands, contracts, and bounces back repeatedly over infinite time. Each cycle might have different properties, different laws of physics, different values for fundamental constants. We might be living in just one phase of an eternal cosmic cycle. But these are all speculations based on models and equations. The truth is we don't know what will happen because we don't understand dark energy. Every measurement we make, every observation we conduct, is an attempt to constrain the properties of this mysterious phenomenon. Scientists are pursuing multiple approaches to studying dark energy. Large surveys map the distribution of galaxies across cosmic history, looking for subtle effects of dark energy on how structure formed and evolved in the universe. Observations of the cosmic microwave background radiation provide information about the composition and geometry of the universe, helping to constrain dark energy's properties. Detailed studies of supernovae continue to refine our measurements of cosmic acceleration. New experiments search for any signs that dark energy is changing over time or varying from place to place. Gravitational wave detectors like LIGO and Virgo are opening up entirely new ways to measure cosmic distances and expansion rates. Space telescopes and ground-based observatories are pushing the boundaries of what we can observe, looking deeper into space and further back in time. One of the most ambitious efforts is the Dark Energy Survey, which has mapped hundreds of millions of galaxies across a large portion of the sky. By studying how galaxies cluster together and how their light is bent by the gravity of intervening matter through a process called gravitational lensing, cosmologists can infer the distribution of both dark matter and the influence of dark energy. The Euclid Space Telescope, launched by the European Space Agency, is designed to map the geometry of the dark universe, measuring the shapes and positions of billions of galaxies to trace the history of cosmic expansion and the growth of cosmic structure. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field surveys to investigate dark energy through multiple techniques. Ground-based projects like the Vera C. Rubin Observatory, with its Large Synoptic Survey Telescope, will observe the entire visible sky every few nights, tracking how the universe changes over time and providing unprecedented data on supernovae, galaxy distributions, and other cosmic phenomena. These experiments are designed to answer crucial questions about dark energy. Is it truly constant, or does it evolve over time? If it evolves, how? Does it have the same strength in all directions and all locations, or could there be variations across the universe? How precisely can we measure the equation of state of dark energy, the relationship between its pressure and density that determines how it affects cosmic expansion? The equation of state is characterized by a parameter called W. For a cosmological constant, W equals -1. If dark energy is something else, W might be different or might change over time. Current observations constrain WES to be very close to -1, but the uncertainties are still large enough that we can't definitively rule out other possibilities. Improving these measurements is one of the highest priorities in cosmology because the nature of dark energy determines not just the fate of the universe, but potentially reveals new physics beyond our current theories. Have you ever wondered what it would mean for our understanding of reality if we discovered that dark energy is not a cosmological constant, but something dynamic and changing? Such a discovery would revolutionize physics. It would mean there's a new field permeating all of space, something that has gone completely undetected in every laboratory experiment ever conducted. This field would interact with gravity and space-time, yet be so weakly coupled to ordinary matter that we've never noticed it despite the exquisite precision of our instruments. Understanding this field could unlock new physics that bridges quantum mechanics and general relativity, potentially pointing the way toward a unified theory that describes all forces and particles in a single framework. It might explain other mysteries, like why the fundamental constants of nature have the values they do, or why the universe contains matter rather than equal amounts of matter and antimatter. Or it could reveal that our universe is just one of countless others in a vast multiverse, each with different properties determined by the local behavior of quintessence-like fields. The multiverse brings us to one of the most controversial ideas related to dark energy, the anthropic principle. The value of dark energy seems remarkably fine-tuned for the existence of life. If dark energy were much larger, it would have dominated the universe much earlier, preventing galaxies and stars from forming. Without stars, there would be no heavy elements, no planets, no chemistry complex enough for life. If dark energy were negative rather than positive, the universe might have recollapsed before stars could form. The observed value of dark energy, while vastly smaller than naive quantum mechanics predicts, is still in the narrow range that allows for a universe with structure, stars, and potentially life. Some physicists argue that this is not a coincidence. They propose that there might be a vast number of universes, perhaps an infinite number, each with different values for fundamental constants including dark energy. Most of these universes would be sterile, unable to support complexity. We find ourselves in one of the rare universes where dark energy has a suitable value simply because we couldn't exist in any of the others. This is the anthropic explanation. Our observations are biased by the requirement of our own existence. Many physicists find the anthropic principle deeply unsatisfying. It seems to give up on finding a fundamental explanation for why dark energy has the value it does, instead appealing to a selection effect. It's also very difficult, or perhaps impossible, to test. If the other universes in the multiverse are forever beyond our reach, causally disconnected from our own, then the multiverse hypothesis makes no testable predictions. It becomes more philosophy than physics. Yet some versions of modern theoretical physics, particularly certain interpretations of string theory and cosmic inflation, naturally predict a multiverse with varying constants. These theories suggest that the very early universe underwent a period of extremely rapid expansion called inflation, which smoothed out the universe and generated the seeds of all cosmic structure. Different regions of space could have emerged from inflation with different properties, essentially becoming separate universes. If this is true, the multiverse is a consequence of well-motivated physical theories, not just speculation. But testing these ideas remains extraordinarily challenging. The quest to understand dark energy has led physicists to some of the strangest ideas ever seriously considered. One particularly exotic proposal suggests that dark energy might be connected to extra dimensions of space beyond the three we experience. String theory, an attempt to unify quantum mechanics and gravity, requires additional spatial dimensions, usually 6 or 7 beyond our familiar 3. These extra dimensions are thought to be curled up into shapes so tiny that we can't perceive them. But what if some of these dimensions are large, or at least different in character from what we've assumed? Modifications to how gravity behaves in higher dimensional space could potentially explain the cosmic acceleration we attribute to dark energy. In some models, gravity can leak into extra dimensions on large scales, making it appear weaker and potentially mimicking the effects of dark energy. These are highly speculative ideas, and testing them requires making precise measurements of gravity on cosmic scales, something that's extraordinarily difficult. Another intriguing possibility is that dark energy is related to the quantum information content of the universe. The holographic principle, emerging from studies of black hole thermodynamics and quantum gravity, suggests that the information contained in a volume of space can be thought of as encoded on the boundary of that region, like a hologram. Some researchers have speculated that dark energy might be a consequence of this holographic nature of reality. If the universe is fundamentally holographic, the energy density that manifests as dark energy could be related to the information content of the cosmic horizon. These ideas are at the cutting edge of theoretical physics, blending quantum mechanics, gravity, and information theory in ways that challenge our most basic assumptions about the nature of space, time, and reality. They remain largely speculative, but they illustrate how deeply the mystery of dark energy cuts into fundamental physics. Consider the philosophical implications of living in a universe dominated by dark energy. We've constructed our understanding of reality based on what we can observe and measure. The scientific method relies on empirical evidence, on testing hypotheses against observations. But dark energy reveals itself only through its most macroscopic effect, the acceleration of cosmic expansion. We can't examine it in a laboratory. We can't isolate it or study its properties directly. We can only infer its existence from its gravitational influence on the largest scales. What if there are other fundamental aspects of reality that we're missing because they don't manifest in ways we can currently detect? Dark energy and dark matter together constitute 95% of the universe's content, and both are invisible to us except through gravity. What else might be out there, hidden in plain sight, affecting the universe in ways we haven't yet recognized? This raises profound questions about the limits of human knowledge. Are there aspects of the universe that are fundamentally unknowable, not just in practice but in principle? Could there be phenomena that don't interact with matter or energy in any way we can detect, making them forever beyond the reach of scientific inquiry? Or will future advances in technology and theory eventually illuminate these dark corners of the cosmos? The history of science is filled with examples of phenomena that seemed mysterious or impossible to study until new tools or new ideas provided breakthroughs. Atoms were once purely theoretical. Gravitational waves were predicted by Einstein in 1916, but not detected until 2015. The expansion of the universe was completely unknown until less than a century ago. Perhaps dark energy will eventually be understood as clearly as we now understand electromagnetism or thermodynamics. Or perhaps it will remain mysterious, a reminder that the universe is under no obligation to be comprehensible to human minds. Let's explore some of the specific observations and measurements that have shaped our understanding of dark energy. The original supernova observations that revealed cosmic acceleration have been refined and extended over the past 25 years. Astronomers have now observed over 1,000 Type Ia supernovae at various distances, painting a detailed picture of the universe's expansion history. These observations consistently show that the expansion has been accelerating for roughly the past 5 billion years. Before that, the universe was actually decelerating, as expected, because matter, both ordinary and dark, dominated the universe's energy content. But as the universe expanded and matter became more dilute, its gravitational influence weakened. Meanwhile, dark energy, if it's a cosmological constant, maintains the same density even as space expands. Eventually, around 5 billion years ago, dark energy became dominant, and the expansion began to accelerate. We live in the era when dark energy is taking over the universe. The cosmic microwave background radiation provides another crucial line of evidence. This faint glow of photons, released when the universe was only 380,000 years old, carries an imprint of the universe's composition and geometry. Tiny temperature fluctuations in the CMB, differences of only a few parts in 100,000, reflect density variations in the early universe that would later grow into galaxies and galaxy clusters. The detailed pattern of these fluctuations depends on several factors, including the curvature of space, the density of ordinary matter, the density of dark matter, and the density of dark energy. By measuring the CMB with high precision, satellites like COBE, WMAP, and Planck have determined the composition of the universe with remarkable accuracy. These measurements confirm that dark energy makes up about 68% of the universe's total energy density. Dark matter accounts for about 27%, and ordinary matter makes up only about 5%. The CMB also tells us that the geometry of the universe is very close to flat, meaning that parallel lines will remain parallel forever, rather than converging or diverging as they would in curved space. Observations of how galaxies cluster together across cosmic time provide yet another independent probe of dark energy. The distribution of galaxies is not random. Gravity causes matter to clump together, with galaxies forming along vast filaments and sheets surrounding enormous voids. The rate at which this structure grows depends on the competition between gravity, which pulls matter together, and cosmic expansion, which pulls it apart. Dark energy affects how fast the universe expands, which in turn affects how quickly structure grows. By mapping the three-dimensional distribution of galaxies at different epochs in cosmic history, astronomers can trace how structure formation has evolved and use this to constrain the properties of dark energy. Large galaxy surveys like the Sloan Digital Sky Survey, the 2-degree Field Galaxy Redshift Survey, and more recent projects have mapped millions of galaxies, revealing the cosmic web of structure in exquisite detail. The pattern of clustering matches predictions of a universe dominated by dark matter and dark energy, providing strong confirmation of this picture. Gravitational lensing offers yet another tool for studying dark energy. Einstein's general relativity predicts that massive objects bend the path of light passing near them. This effect can be dramatic. When a massive galaxy cluster lies between us and a more distant galaxy, the cluster's gravity can bend the light from the background galaxy, distorting its image into arcs or even multiple images. This is called strong gravitational lensing. But there's also a weaker effect, where the shapes of distant galaxies are slightly distorted by all the matter along the line of sight. By measuring the shapes of millions of galaxies and looking for statistical patterns in how they're distorted, astronomers can map the distribution of all matter, both visible and dark, between us and those galaxies. This technique, called weak gravitational lensing, is sensitive to both dark matter and dark energy. Dark matter creates the gravitational potential wells that bend light, while dark energy affects the geometry of space and the growth of structure, both of which influence the lensing signal. Combining weak lensing measurements with other observations provides powerful constraints on dark energy. One of the most exciting recent developments in cosmology is the use of baryon acoustic oscillations to measure cosmic expansion. In the early universe, before the CMB was released, the cosmos was a hot plasma of photons, electrons, and atomic nuclei. Sound waves propagated through this plasma, creating oscillations in the density of matter. When the universe cooled enough for atoms to form, these sound waves froze into the distribution of matter, leaving a characteristic scale imprinted on the pattern of galaxy clustering. This scale, about 500 million light-years, acts as a standard ruler. By measuring how large this scale appears at different distances, astronomers can trace how the universe has expanded over time, similar to how supernovae are used as standard candles. Baryon acoustic oscillations have been detected in large galaxy surveys and provide measurements of cosmic expansion that are independent of supernovae and other methods. The results agree with the picture of an accelerating universe driven by dark energy. All of these different lines of evidence, supernovae, the cosmic microwave background, galaxy clustering, gravitational lensing, baryon acoustic oscillations, point to the same conclusion. The universe is dominated by dark energy, and this dark energy is causing cosmic expansion to accelerate. The convergence of multiple independent observations is what gives cosmologists confidence that dark energy is real, despite how mysterious it is. This is how science works at its best. No single observation is perfect. Every measurement has uncertainties and potential systematic errors. But when completely different techniques, based on different physics and subject to different sources of error, all point to the same answer, that answer is likely to be correct. Dark energy has gone from a shocking and controversial discovery to an accepted component of the standard model of cosmology, not because anyone fully understands it, but because the evidence for its existence is overwhelming. Yet accepting that dark energy exists doesn't mean we understand what it is. The distinction is crucial. We have excellent measurements of how much dark energy there is and how it affects the universe. We know that it makes up about 68% of the cosmic energy budget. We know that it causes the expansion of the universe to accelerate. We know that its density appears to be nearly constant as the universe expands, consistent with a cosmological constant. But we don't know what it is. We don't know why it exists. We don't know why it has the value it does. We don't know whether it's truly constant or evolving. We don't know if it's a property of space itself or a field that fills space. We don't know whether Einstein's general relativity is the correct theory of gravity on cosmic scales, or whether the apparent effects of dark energy are actually telling us that we need a new theory of gravity. These are the questions driving current research. Imagine if we discovered that dark energy is not constant but changing. Even a small time variation in dark energy would revolutionize cosmology. It would tell us that dark energy is not simply a cosmological constant but some kind of dynamical field. This would open up a host of new questions. What determines the properties of this field? How does it interact with other fields and particles? Where did it come from? Is it related to the field that drove cosmic inflation in the very early universe? Inflation is a period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang, stretching the universe by an enormous factor and setting the stage for all subsequent structure formation. The field that drove inflation, often called the inflaton, is also hypothetical and mysterious. Could dark energy be a cousin of the inflaton, or even the same field in a different regime? These questions connect dark energy to some of the deepest problems in cosmology and fundamental physics. The connection to inflation raises another intriguing possibility. Some models of inflation predict that it never truly ends everywhere. Instead, different regions of space stop inflating at different times, with each region becoming a separate bubble universe. In regions where inflation continues, space keeps expanding exponentially, spawning more bubble universes in an eternal process. This scenario, called eternal inflation, naturally produces a multiverse. Each bubble universe could have different properties, different values for fundamental constants, determined by how the inflaton field and other fields settle down after inflation ends in that region. If dark energy is related to such a field, its value could be different in different bubble universes. We observe the value we do because we exist in a bubble where that value allows for structure and life. This would be an anthropic explanation for dark energy's value, but grounded in a physical mechanism, eternal inflation, that's predicted by well-motivated theories. Testing these ideas is extraordinarily difficult because we can't directly observe other bubble universes. They're beyond our cosmic horizon, and if eternal inflation is correct, they always will be. But some researchers have looked for indirect evidence. If our bubble universe collided with another bubble universe in the distant past, it might have left an imprint on the cosmic microwave background, a circular pattern of temperature variations. Searches for such collision signatures have so far come up empty, but the absence of evidence isn't evidence of absence, especially when we don't know exactly what to look for or how likely such collisions are. The multiverse remains a speculative idea, fascinating and potentially explanatory, but currently beyond the reach of definitive testing. This puts it in an uncomfortable place scientifically, neither clearly confirmed nor ruled out, and possibly unfalsifiable. Let's consider an alternative approach to the dark energy mystery. Instead of assuming that general relativity is correct and that we're missing some form of energy, what if we assume that the inventory of energy is complete and that we need to modify gravity? This is the strategy behind modified gravity theories. One well-known example is called MOND, Modified Newtonian Dynamics, which was originally proposed to explain galaxy rotation curves without dark matter. MOND suggests that gravity behaves differently than Newton's law predicts when accelerations are extremely small, like those experienced by stars in the outer parts of galaxies. While MOND has had some success in explaining galaxy dynamics, it struggles to account for other observations, like gravitational lensing by galaxy clusters and the pattern of the cosmic microwave background. Extensions of MOND that incorporate relativity, like TeVis, have been developed, but they face their own challenges. Other modified gravity theories take different approaches. Some add extra fields or modify the way space-time curvature relates to matter and energy. Others invoke extra dimensions or changes to gravity at very large distances. One idea, called DGP gravity, named after physicists Valley, Gabadads, and Poreti, suggests that we live on a four-dimensional surface, a brain embedded in a five-dimensional spacetime. Gravity can leak into the extra dimension on sufficiently large scales, weakening its effective strength and potentially leading to accelerated expansion without dark energy. These theories make predictions that differ from general relativity, and astronomers are searching for observational signatures that could distinguish between dark energy and modified gravity. For instance, modified gravity theories generally predict that the way matter clusters and the way light is bent by gravity should be related in a different way than in general relativity. By measuring both structure growth and gravitational lensing and comparing them, we might be able to tell whether we're seeing dark energy or modified gravity. So far, observations favor general relativity plus dark energy over modified gravity alternatives. But the tests are not yet precise enough to rule out all possibilities. This remains an active area of research. It's worth emphasizing that modifying gravity is a radical step. General relativity is one of the most well-tested theories in all of physics. It makes predictions that have been confirmed to exquisite precision, from the orbit of Mercury to the timing of pulsars to the detection of gravitational waves. To replace or modify, it requires not just explaining cosmic acceleration, but also reproducing all of general relativity's successes in other regimes. This is a high bar to clear, and it's one reason why many physicists favor the dark energy explanation. It requires adding something new to the universe, which is strange enough, but it doesn't require breaking a theory that works so well in so many other contexts. Still, the fact that dark energy is so mysterious keeps the door open for modified gravity. If we can't explain what dark energy is, maybe the real problem is with our theory of gravity. There's a fascinating historical parallel here. In the 19th century, astronomers noticed that the orbit of Mercury didn't quite match predictions based on Newton's law of gravity. Mercury's elliptical orbit precesses, meaning the point of closest approach to the Sun slowly rotates over time. Most of this precession could be explained by the gravitational influence of other planets, but there was a small discrepancy. One hypothesis was that there was an undiscovered planet closer to the Sun than Mercury, which was tentatively named Vulcan. Searches for Vulcan came up empty. The real explanation came when Einstein developed general relativity, which makes slightly different predictions than Newtonian gravity for orbits in strong gravitational fields. When Einstein applied his new theory to Mercury's orbit, the discrepancy vanished. The problem wasn't a missing planet. It was that Newton's theory, while extraordinarily accurate in most situations, was slightly wrong. Could we be in a similar situation with dark energy? Are we postulating something that doesn't exist because we're using a slightly wrong theory of gravity? Or is dark energy real, and we just need to find the right way to detect and understand it? Another avenue of research involves looking for any interactions between dark energy and other components of the universe. So far, dark energy appears to interact with ordinary matter and dark matter only through gravity. It doesn't emit, absorb, or scatter light. It doesn't clump together like matter does. It seems to be perfectly smooth and uniform. But what if there are subtle interactions we haven't yet detected? Some models propose that dark energy could interact with dark matter, affecting how dark matter clusters. Others suggest that dark energy might interact with neutrinos, the nearly massless particles that zip through the universe in vast numbers. If such interactions exist, they would leave imprints on the distribution of galaxies, the cosmic microwave background, or other observables. Searches for these effects push the boundaries of observational cosmology, requiring precise measurements and careful analysis to tease out tiny signals from noise and systematics. Neutrinos themselves are an interesting case. These particles barely interact with ordinary matter, passing through planets and stars as if they weren't there. For decades, they were thought to be massless, but experiments have shown that they have a tiny mass. This means that neutrinos contribute to the matter density of the universe, though only a small amount. The sum of the masses of the three types of neutrinos is constrained by cosmological observations to be less than about 1/10 of an electron volt, which is extraordinarily light. To put this in perspective, an electron has a mass of about 500,000 electron volts. Neutrinos are at least 5 million times lighter. Yet because they were produced in such enormous numbers in the early universe, they have measurable effects on structure formation. Interestingly, the same cosmological observations that constrain dark energy also constrain neutrino masses, illustrating how interconnected these mysteries are. Think about the tools and methods that have brought us to this point in our understanding. The discovery of dark energy was made possible by technological advances in telescopes, detectors, and computers. Building cameras sensitive enough to detect the faint light of distant supernovae, telescopes large enough to collect that light, and algorithms sophisticated enough to find supernovae among millions of stars required decades of development. Analyzing the cosmic microwave background required satellites that could measure temperature differences of millionths of a degree across the sky and computational techniques to extract cosmological information from the data. Mapping millions of galaxies required automated survey telescopes and enormous databases. Our understanding of the universe is intimately tied to the tools we build to explore it. Every advance in technology opens new windows on the cosmos and raises new questions. What new tools will we need to finally understand dark energy? Some proposed experiments are truly ambitious. Space-based missions could measure cosmic distances and expansion with unprecedented precision, potentially detecting time variations in dark energy or deviations from general relativity. Ground-based telescopes with ever larger mirrors could observe fainter and more distant objects, probing earlier epochs in cosmic history. Next-generation particle colliders might create conditions that shed light on the quantum vacuum and its energy. Gravitational wave detectors could measure cosmic expansion using entirely different techniques, providing independent checks on other methods. Advances in theoretical physics might reveal new symmetries or principles that explain why dark energy has the value it does. The answers might come from astronomy, or from particle physics, or from mathematics, or from a combination of all three. The mystery of dark energy touches so many areas of physics that progress could come from unexpected directions. Consider the social and scientific context in which this research happens. Studying dark energy requires large collaborations of scientists from around the world, working together over many years. Building a space telescope or conducting a major survey involves hundreds or thousands of people. Astronomers, engineers, software developers, project managers, and many others. The cost of these projects can be hundreds of millions or even billions of dollars, requiring funding from governments and space agencies. Decisions about which projects to pursue involve weighing scientific priorities, technical feasibility, and budget constraints. The process is competitive, with many worthy projects vying for limited resources. Yet despite these challenges, the field has made remarkable progress. The discovery of dark energy is one of the great scientific achievements of recent decades, and the effort to understand it continues to drive innovation in observational techniques, data analysis, and theoretical physics. The human element of this scientific endeavor is worth reflecting on. The astronomers who discovered cosmic acceleration didn't set out expecting to find dark energy. They thought they were measuring how much cosmic expansion was slowing down. The fact that they found acceleration instead is a testament to the power of empirical science. Nature surprised them. The universe revealed something completely unexpected. This is science at its most exciting, when observations overturn assumptions and force us to revise our understanding. It's also humbling. Despite all our sophisticated theories and powerful telescopes, the universe can still shock us. Dark energy is a reminder that we don't have all the answers, that there are profound mysteries yet to be solved, and that the cosmos is stranger and more wonderful than we imagined. What can we, as individuals, take from the story of dark energy? On one level, it's a story about the universe, about cosmic expansion and the fate of everything that exists. But it's also a story about human curiosity and ingenuity, about our drive to understand the world around us, even when that world extends billions of light years beyond our planet. It's a story about how we deal with mystery and uncertainty, how we build knowledge from observations and reason, and how we confront the limits of what we know. Dark energy challenges us to think deeply about reality itself, about what exists and how we can come to know it. It reminds us that the universe doesn't care about our preconceptions. It is what it is, and our job is to figure it out as best we can, using whatever tools and insights we can muster. The philosophical implications extend even further. Dark energy raises questions about why the universe exists at all and why it has the properties it does. These are ancient questions, pondered by philosophers and theologians for millennia. Modern cosmology doesn't necessarily answer them, but it reframes them in precise, scientific terms. Why does the cosmological constant have the value it does? Why is there something rather than nothing? Why is the universe comprehensible to beings like us? These questions sit at the boundary between physics and philosophy. Some scientists think physics can eventually answer all of them. Others think some questions will always remain beyond the reach of science. Dark energy doesn't resolve this debate, but it sharpens it, giving us a concrete example of a deep mystery at the heart of physical reality. Let's revisit the timeline of discovery and see how our understanding has evolved. Before 1998, most cosmologists assumed the universe's expansion was slowing down. The main debate was whether the universe had enough matter to eventually recollapse or whether it would expand forever. The discovery of acceleration was a shock that upended this picture. In the years immediately following, there was intense scrutiny of the supernova results. Were they really seeing acceleration, or could there be some other explanation? Perhaps distant supernovae were intrinsically dimmer than nearby ones, making them appear farther away than they actually were. Maybe dust in intergalactic space was dimming their light. Maybe the assumption that all Type Ia supernovae have the same brightness was wrong. These possibilities were carefully examined. Astronomers studied supernovae at different wavelengths to check for dust effects. They looked for correlations between supernova brightness and the properties of their host galaxies. They refined their understanding of what makes a Type Ia supernova and how to correct for small variations in brightness. The result of all this scrutiny was that the evidence for acceleration held up. Alternative explanations didn't work. By the mid-2000s, other lines of evidence were confirming the picture. Measurements of the cosmic microwave background from the WMAP satellite showed that the universe is flat, which, combined with measurements of the matter density, implied that something else, dark energy, must make up the difference. Observations of galaxy clustering and baryon acoustic oscillations provided independent confirmation. By the time the Nobel Prize was awarded in 2011, dark energy had gone from a controversial claim to an established fact. But established facts can still be mysterious. Accepting that dark energy exists doesn't mean understanding what it is. In the years since, the focus has shifted from confirming acceleration to measuring the properties of dark energy more precisely and searching for clues to its nature. Current observations constrain the equation of state parameter West to be close to -1, the value for a cosmological constant, but with uncertainties of several percent. Future observations aim to reduce these uncertainties to less than 1% or even a fraction of 1%. If dark energy is truly constant, then W should be exactly -1 at all times. If W is measured to be different from -1, or if it's shown to change over time, that would rule out the cosmological constant and point toward quintessence or some other exotic explanation. Even measuring that W is exactly -1 to very high precision would be scientifically valuable, because it would pose the cosmological constant problem in even starker terms. Why is the vacuum energy so incredibly small compared to what quantum mechanics predicts, yet still large enough to dominate the universe today? Some of the most speculative ideas about dark energy connect it to the ultimate theory of quantum gravity, the long-sought framework that would unify quantum mechanics and general relativity. One candidate for such a theory is string theory. which proposes that the fundamental constituents of nature are not point particles but tiny vibrating strings. String theory has had some remarkable mathematical successes, and it naturally incorporates gravity, but it also makes some strange predictions, like requiring extra dimensions of space. One of the challenges for string theory has been making contact with observable physics. The theory has a vast landscape of possible solutions, perhaps 10 to the power of 500 or more, each corresponding to a different way the extra dimensions can be configured in different values for the constants of nature, including the cosmological constant. Some researchers view this landscape as a problem, a sign that string theory doesn't make unique predictions. Others see it as an opportunity, suggesting that different solutions correspond to different bubble universes in an eternally inflating multiverse. Our universe would correspond to one particular solution, one particular point in the landscape, chosen not by fundamental principles but by the anthropic requirement that it supports observers. Loop quantum gravity, another approach to quantum gravity, takes a different tack. Instead of starting with strings, it starts with the fabric of spacetime itself and tries to quantize it, applying the principles of quantum mechanics to the geometry of the universe. In loop quantum gravity, space is not continuous but made of discrete loops at the tiniest scales, the Planck scale, about 10 to the power of minus 35 meters. At these scales, our usual notions of space and time break down. Some researchers have explored whether loop quantum gravity might explain dark energy or provide alternatives to the Big Bang singularity, like a cosmic bounce from a previous contracting phase. These ideas are still being developed and debated. Quantum gravity remains an unsolved problem, and it's unclear whether string theory, loop quantum gravity, or some other approach will ultimately succeed. But whatever the correct theory of quantum gravity turns out to be, it will need to account for dark energy. Here's something to ponder. If dark energy remains constant and continues to drive accelerated expansion, the distant future of the universe will be profoundly different from the present. We've already discussed the heat death and the eventual evaporation of all black holes. But there's another consequence worth considering. As space expands faster and faster, regions of space that are currently within our observable universe will eventually cross the cosmic horizon and disappear from view. The observable universe will actually shrink, even as the universe as a whole expands. This seems paradoxical, but it makes sense when you remember that the observable universe is limited by the distance light can travel in the age of the universe, adjusted for cosmic expansion. If space is expanding fast enough, light from distant regions will never catch up to us. Those regions will be forever beyond our reach, not because they're too far away in a static sense, but because the space between us and them is expanding too fast for light to cross. This means that future civilizations, if any exist, will have access to less information about the universe than we do. They'll live in an ever more isolated cosmos. Imagine trying to do cosmology in such a far future. With no access to distant galaxies, no cosmic microwave background, no evidence of the Big Bang, what could future scientists learn about the universe? They would see only their local group of galaxies, possibly merged into a single large galaxy, surrounded by darkness. They might develop sophisticated theories of physics, but without the observational evidence we have, they would likely reach very different conclusions about cosmology. They might assume the universe is static and eternal, consisting only of their galaxy. They would have no way of knowing about dark energy, about cosmic expansion, about the Big Bang. The evidence would have literally expanded away from them. This raises an unsettling question. What crucial evidence has already expanded beyond our cosmic horizon? What could we have learned about the universe if we had been around earlier, when more of it was observable? Are there secrets of the cosmos that we'll never know because the relevant information is no longer accessible to us? This connects to a broader point about the nature of scientific knowledge. What we can learn about the universe depends not just on our cleverness and our tools, but on our location in space and time. We're fortunate to live in an era when the cosmic microwave background is still detectable, when distant galaxies are still visible, when the expansion of the universe is fast enough to measure but not so fast that everything has disappeared over the horizon. If humans had evolved billions of years earlier or later, we would have a very different view of the cosmos. This suggests that scientific knowledge is contingent in ways we don't often appreciate. It's shaped by the particular moment in cosmic history when we happen to exist. Other civilizations at other times or places might have access to different information and develop different understandings of the universe, not because they're smarter or less smart than we are, but because they're seeing different pieces of the cosmic puzzle. Let's think about the energy scales involved in dark energy. The energy density of dark energy is extraordinarily small by particle physics standards, about 10 to the power of -9 joules per cubic meter. To put this in perspective, the energy in the mass of a single proton, using Einstein's E equals mc squared, is about 10 to the power of -10 joules. So a cubic meter of space, due to dark energy, has energy equivalent to about 10 protons worth of mass. That doesn't sound like much, and on small scales it isn't. The dark energy in your body, or in the Earth, or even in the solar system, is negligible compared to the energy in matter. But when you multiply this tiny energy density by the enormous volume of the observable universe, the total amount of dark energy becomes staggering. And because this energy density doesn't dilute as the universe expands, it remains constant even as the volume grows, meaning the total amount of dark energy in the universe is increasing over time. This is one of the strange features of dark energy that makes it so different from ordinary matter or radiation. Another way to think about dark energy is in terms of the pressure it exerts. In general relativity, both energy density and pressure contribute to gravity. Positive pressure, like the pressure in a gas, actually enhances gravity, pulling things together. Negative pressure, which sounds bizarre but is perfectly allowed mathematically, creates a repulsive gravitational effect. Dark energy has a very unusual equation of state. Its pressure is negative, and in fact, for a cosmological constant, the pressure is exactly equal to minus the energy density. This negative pressure is what drives the accelerated expansion. It's as if the vacuum is pushing outward on itself, causing space to expand faster and faster. This is completely unlike anything in our everyday experience. We're familiar with positive pressure, like air pushing on the walls of a balloon, but negative pressure is alien to our intuition. Yet this is what the equations of general relativity predict for a cosmological constant, and it's what the observations of cosmic acceleration require. The philosophical notion of nothingness takes on new meaning in light of dark energy. We tend to think of empty space as truly empty, as nothing. But quantum mechanics tells us that the vacuum is filled with fluctuating fields, virtual particles popping in and out of existence. General relativity now tells us that this empty space has energy and exerts pressure, enough to dominate the universe and determine its fate. Nothing, it turns out, is something. The vacuum is an active, dynamic entity with physical consequences. This challenges our intuitions about what it means for something to exist or not exist. If empty space has properties like energy density and pressure, if it can cause galaxies to accelerate away from each other, in what sense is it empty? This is not just a semantic question. It cuts to the heart of what we mean by physical reality. Dark energy forces us to expand our conception of what can be real and what can have causal effects on the world. Let's explore one more speculative idea: the possibility that dark energy could be harnessed or manipulated. This is pure science fiction at the moment, but it's worth considering, if only to understand why it's so difficult. If dark energy is a form of energy filling all of space, could an advanced civilization extract that energy and use it? The problem is that dark energy is extraordinarily dilute and doesn't seem to interact with ordinary matter except through gravity. There's no known mechanism by which you could grab dark energy and do work with it. Moreover, because dark energy exerts negative pressure, trying to extract energy from it would require doing work against that negative pressure, and it's unclear if you could get a net positive energy output. Some speculative theories in physics suggest that very advanced civilizations might be able to manipulate the vacuum energy or the cosmological constant, perhaps even creating regions of space with different values. But these ideas are far beyond our current understanding and technology. They belong more to the realm of philosophical thought experiments than practical engineering. Still, it's interesting to think about what a civilization capable of manipulating dark energy could do. If you could change the strength of dark energy in a localized region, you might be able to control the expansion of space itself, perhaps creating propulsion systems that don't require conventional fuel. If you could create regions with different values of the cosmological constant, you might be able to build new kinds of structures or even new pocket universes. Some physicists have even speculated that the Big Bang itself might have been artificially triggered by a previous civilization manipulating the vacuum. These ideas are wildly speculative, and there's no evidence for any of them, but they illustrate how profoundly dark energy challenges our understanding of what's possible. We live in a universe where 70% of the energy content is something we don't understand. Who knows what that something might allow if we ever figure out how to interact with it? Coming back to firmer ground, let's consider what the next few decades of research might bring. Several major observational projects are underway or planned that will significantly improve our understanding of dark energy. The Vera C. Rubin Observatory, when it begins operations, will survey the entire southern sky every few nights, discovering thousands of supernovae and mapping billions of galaxies. This will provide unprecedented data on cosmic expansion and structure growth. The Nancy Grace Roman Space Telescope will conduct deep surveys from space, measuring distances to galaxies with high precision and studying gravitational lensing. The European Space Agency's Euclid mission is already collecting data to map the geometry of the universe. Ground-based observatories like the Subaru telescope with its Hyper-Suprime-Cam and future facilities like the Extremely Large Telescope will push observations to even greater distances and fainter objects. New techniques, like using gravitational wave observations of colliding black holes and neutron stars as cosmic distance indicators, could provide completely independent measurements of cosmic expansion. On the theoretical side, physicists continue to develop and refine models of dark energy and modified gravity. They're exploring connections to quantum field theory, string theory, and cosmological inflation. They're using supercomputers to run detailed simulations of cosmic structure formation, comparing predictions of different models to observations. They're looking for subtle signatures that could distinguish between a cosmological constant and dynamical dark energy, or between dark energy and modified gravity. The synergy between observation and theory is crucial. Observations provide the data that theories must explain, while theories suggest new observables to look for and new ways to interpret data. Progress comes from the interplay between the two. Another way to think about dark energy is in terms of the pressure it exerts. In general relativity, both energy density and pressure contribute to gravity. Positive pressure, like the pressure in a gas, actually enhances gravity, pulling things together. Negative pressure, which sounds bizarre but is perfectly allowed mathematically, creates a repulsive gravitational effect. Dark energy has a very unusual equation of state. Its pressure is negative, and in fact, for a cosmological constant, the pressure is exactly equal to minus the energy density. This negative pressure is what drives the accelerated expansion. It's as if the vacuum is pushing outward on itself, causing space to expand faster and faster. This is completely unlike anything in our everyday experience. We're familiar with positive pressure, like air pushing on the walls of a balloon, but negative pressure is alien to our intuition. Yet this is what the equations of general relativity predict for a cosmological constant, and it's what the observations of cosmic acceleration require. The philosophical notion of nothingness takes on new meaning in light of dark energy. We tend to think of empty space as truly empty, as nothing. But quantum mechanics tells us that the vacuum is filled with fluctuating fields, virtual particles popping in and out of existence. General relativity now tells us that this empty space has energy and exerts pressure, enough to dominate the universe and determine its fate. Nothing, it turns out, is something. The vacuum is an active, dynamic entity with physical consequences. This challenges our intuitions about what it means for something to exist or not exist. If empty space has properties like energy density and pressure, If it can cause galaxies to accelerate away from each other, in what sense is it empty? This is not just a semantic question. It cuts to the heart of what we mean by physical reality. Dark energy forces us to expand our conception of what can be real and what can have causal effects on the world. Let's explore one more speculative idea: the possibility that dark energy could be harnessed or manipulated. This is pure science fiction at the moment, but it's worth considering, if only to understand why it's so difficult. If dark energy is a form of energy filling all of space, could an advanced civilization extract that energy and use it? The problem is that dark energy is extraordinarily dilute and doesn't seem to interact with ordinary matter except through gravity. There's no known mechanism by which you could grab dark energy and do work with it. Moreover, because dark energy exerts negative pressure, trying to extract energy from it would require doing work against that negative pressure, and it's unclear if you could get a net positive energy output. Some speculative theories in physics suggest that very advanced civilizations might be able to manipulate the vacuum energy or the cosmological constant, perhaps even creating regions of space with different values. But these ideas are far beyond our current understanding and technology. They belong more to the realm of philosophical thought experiments than practical engineering. Still, it's interesting to think about what a civilization capable of manipulating dark energy could do. If you could change the strength of dark energy in a localized region, you might be able to control the expansion of space itself, perhaps creating propulsion systems that don't require conventional fuel. If you could create regions with different values of the cosmological constant, you might be able to build new kinds of structures or even new pocket universes. Some physicists have even speculated that the Big Bang itself might have been artificially triggered by a previous civilization manipulating the vacuum. These ideas are wildly speculative, and there's no evidence for any of them, but they illustrate how profoundly dark energy challenges our understanding of what's possible. We live in a universe where 70% of the energy content is something we don't understand. Who knows what that something might allow, if we ever figure out how to interact with it. Coming back to firmer ground, let's consider what the next few decades of research might bring. Several major observational projects are underway or planned that will significantly improve our understanding of dark energy. The Vera C. Rubin Observatory, when it begins operations, will survey the entire southern sky every few nights, discovering thousands of supernovae and mapping billions of galaxies. This will provide unprecedented data on cosmic expansion and structure growth. The Nancy Grace Roman Space Telescope will conduct deep surveys from space, measuring distances to galaxies with high precision and studying gravitational lensing. The European Space Agency's Euclid mission is already collecting data to map the geometry of the universe. Ground-based observatories like the Subaru telescope with its Hyper-Suprime-Cam, and future facilities like the extremely large telescope, will push observations to even greater distances and fainter objects. New techniques, like using gravitational wave observations of colliding black holes and neutron stars as cosmic distance indicators, could provide completely independent measurements of cosmic expansion. On the theoretical side, physicists continue to develop and refine models of dark energy and modified gravity. They're exploring connections to quantum field theory, string theory, and cosmological inflation. They're using supercomputers to run detailed simulations of cosmic structure formation, comparing predictions of different models to observations. They're looking for subtle signatures that could distinguish between a cosmological constant and dynamical dark energy, or between dark energy and modified gravity. The synergy between observation and theory is crucial. Observations provide the data that theories must explain, while theories suggest new observables to look for and new ways to interpret data. Progress comes from the interplay between the two. The story of dark energy is still being written. Every observation adds a new sentence, every theory a new paragraph. We don't know how it will end, whether with a satisfying explanation that ties together all the loose threads or with a deeper recognition of mystery. What we do know is that the universe has surprised us before and will surely surprise us again. Dark energy is a reminder that reality doesn't conform to our expectations, that nature is under no obligation to be simple or comprehensible, and that the cosmos holds secrets we're only beginning to uncover. It's a reminder that the most honest answer to many of the deepest questions is still, we don't know, and that admitting our ignorance is not a failure but the first step toward knowledge. As you contemplate the vastness of space and the mystery of dark energy, consider this. You are made of atoms forged in the hearts of stars, atoms that have existed for billions of years before coming together in the particular arrangement that is you. You are a way for the universe to know itself, a localized pocket of consciousness and curiosity in a cosmos that is mostly empty space and dark energy. You exist at a time when it's possible to discover these truths, to look out into the universe and see not just stars, but the deep structure of reality. That's extraordinary. Dark energy might dominate the cosmos, but it doesn't diminish the wonder of existence or the value of understanding. If anything, it amplifies it, showing us that the universe is far more mysterious and magnificent than we ever imagined, and that the quest to understand it is one of the most profound endeavors we can undertake. The invisible force tearing the universe apart, the 70% of reality we cannot see or touch, the mysterious energy pushing galaxies ever farther apart, this is dark energy. It challenges our deepest theories, threatens our distant future, and reminds us of how much we have yet to learn. It is perhaps the greatest mystery in modern science, and solving it might require rethinking the very foundations of physics. Or perhaps it will remain mysterious, a cosmic riddle that future generations will still be pondering long after we're gone. Either way, dark energy has changed our understanding of the universe forever. We now know that we live in a cosmos dominated by the unknown, a universe that is stranger, more dynamic, and more wondrous than we ever dared to dream. And that, perhaps, is the most important discovery of all.